Hello to everyone. Today we have second day of our conference, the satellite conference of ICBS. First speaker for today it's Robert Weston from Maxwell Institute for Math Science. Welcome.
Thank you. So the Maxwell Institute for Mathematical Sciences. And we often ask our students who Maxwell was, and most of them don't know. So. Okay, so first of all, as usual, I'd like to thank the organizers, for their organization, but also for their huge hospitality. So I've been here the week before this conference, and I was also here a year ago. And during that period, everybody turned up their hospitality to 11, and I really appreciate it. Thank you. So I'm talking about quite an old problem. So in Edinburgh 3 weeks ago, there was a meeting, and Kaliyoshi Tikin was there, and he passed on the advice that the best talk is like the best bread, which is baked the night before. And then another participant, Renat Kadem, disagreed. She said the best baguettes are baked on the morning. Well, in Scotland, we're not very well known for our bread, but we are well known for our whiskey. And the best whiskey is made 30 years before. So in that spirit, I'm discussing quite an old 30-year-old problem, but I hope I have some new insight that I can share with you on it. Okay, so the plan is to give a bit of background, going back to these 30 years, and motivation. And then I want to talk about cyclic representations of quantum affine algebra, a UQSL2 hat, and its Borel subalgebra. And a word of warning, when I say cyclic, these are cyclic in the usual sense, but I mean something different. And I mean that there are finite-dimensional representations that are built in terms of some step operators that act periodically. Okay. And another piece of advice I received recently was from Jimbo, who received it from Cax, which was, don't call them cyclic. Okay, but it's too late. They're called cyclic representations. So I want to talk about properties of these representations and what I call factorization and fusion. And in particular, I want to talk about how these are used and the consequences of these properties for transfer matrices and Q operators and statistical mechanical models. And this is based on a fairly recent paper. Okay, so background. So 35 years ago now, there was a paper by Bajanov and Stroganov in 1990 that established, at least to the stack mech community, a very surprising connection between the 6-vertex model and the Chiral Potts model, which superficially seem like very different types of statistical mechanical models at Q, a root of unity, where Q is going to be associated with UQSL2 hat. And this was sort of very quickly jumped on and generalized in lots of directions, in particular by Date, Jimbo, Miki, Miwa, and then by Bajanov, Stroganov and collaborators. And in turn, this built on previous work on these roots of unity representations by De Concini and Cax. And here's the kind of observation in half a page. And I'm going to go over this in more detail. This is just the introduction. But the essential idea is that if you look at roots of unity of UQSL2 hat, this tilde means it's an centrally extended version that I'll tell you about later on. Then, as well as the representations that come from ASL2 representations, which are just finite integer dimensions, there are new types of representations which are n-dimensional. And these representations, which I call omega here, depend upon not a single spectral parameter, a complex number, but upon 2 points in a higher-genus algebraic curve, which has come to be called the Chiral Potts curve. Okay, so it's a new class of representations. And moreover, for these representations, then an intertwiner, which is a R-check matrix, exists of this form. Oh, sorry, I'm going to attempt to get my pointer up. Yep. So this this R matrix exists, and it factorizes into 4 factors, and each of these factors just swaps one pair of these indices. So there's one that swaps, this pair, and then there's another one that swaps this pair. And if you compose 4 of these, you swap all of them, and you get this factor, this R matrix. And, okay, so big deal. Well, the surprising thing for physics was that these factors encode the Boltzmann weights of the Chiral Potts model, which was an existing model that had come from completely different direction in StatMech. Okay, so that was a surprise, but this work has been really influential, and it's been the inspiration for many, many papers on factorization of various quantities, in particular R matrices, like the type of factorization I just said, but also L operators, that I'll tell you about in a bit, and physically, most importantly, transfer matrices. And probably the most influential work has been the work of Bazhanov, Lukyanov, and Zamolodchikov and others who took this factorization idea and ran with it. And they constructed Q operators doing strange things. Okay. They constructed Q operators and showed how transfer matrices factorize into Q operators. And originally, this was kind of in the context of conformal field theory, but it was very much using these ideas. And then this was generalized and understood algebraically, but in lots of different people. Dokuchov, who was here last week, did an awful lot of work on factorization of R matrices and L operators. And then there was work by both Jimbo, Miwa, Takayama, both Gurman, Klumper, Nirov, Razumov, Wuppertal people, and many, many others. And yeah, so this was a big influential. So let me tell you roughly how this factorization works at generic Q, and then I'll tell you in detail how it works at Q as a root of unity. Okay, so now we're just thinking about Q generic. So the algebraic picture of this Q operator is as follows. So there are a bunch of different representations that come into it. And importantly, Borel subalgebra representations come into it. So you consider infinite-dimensional Borel subalgebra representations, and in particular ones where the Borel subalgebra is just generated by E0, E1, and then the Cartan parts. And you look at representations where these E0, which are highest weight, and E0 and E1 just step up and step down. And if you consider all possible types of UQP plus representations of that form, then almost all of them can be just written as restrictions of the Verma module, except for 2. And those I call rho Z and rho Z bar. And and these can be constructed in various ways. One is in terms of Q oscillators, and that's what Bazhanov, Lukyanov, and Zamolodchikov used. As I said, I'll go into more detail later on. This is just the overview. So then you use these 2 representations to define 2 Q operators. So the standard picture is you go from a representation to L operators, you take products of L operators, and then you take a trace, and that's a transfer matrix or a Q operator. And you can do this with lots of different types of representations. Okay, so Q and Q bar, and again, I'll tell you how this works later on. So Q and Q bar are given as twisted traces of the monodromy matrix over these 2 types of representations. And then there are 3 other representations that come into the story, which most of them are familiar. There's the Verma module. So this is depending upon this weight, this SL2 weight, mu. And also, well, this is the Verma module of UQSL2, which is then pulled back to a representation of the quantum affine algebra using the evaluation homomorphism. We saw that yesterday. So that picks up a spectral parameter. And then you do the same for the 2-dimensional representation of, they just upgraded GoodNotes. And now it does. So you do the same for the 2-dimensional representation of UQSL2, and that gives you a 2-dimensional evaluation representation that's here. Oh, God, I'm going to give up on this. So there's this. And then finally, so those are probably quite familiar. Then there's this other thing which I call a triangular representation that depends upon Z as well. And this, why is it triangular? Well, again, it's of this half-infinite form, and the E1s kill any vector, and the E0s act down. So this is a filtered module. So at any particular level, there's a finite number of modules that sit within it. Okay, so this is what I call a triangular representation. And then the key algebraic content of the whole Q-operator construction for SL2 is just the following. I have this two things. So first of all is I have a Borel subalgebra isomorphism between the Verma module and this triangular representation and the tensor product of these two Q-oscillator representations. Okay, so that you can just establish the fact that there's an isomorphism. And the other thing is there's a UQB plus a Borel subalgebra short exact sequence. Okay, so I have a submodule and the quotient module is given by this. And when you combine this with the L operators that I'll tell you about, then it leads immediately to these factorization conditions. So this transfer matrix is a trace over this space. And then you take a trace of a monodromy matrix over this space, and that factorizes into QQ bar. And the key thing about these triangular representations is that the monodromy matrices are very simple. If I choose a particular weight sector, they're just proportional to the identity. Okay, so the kind of trace over this space is very simple, and so essentially I get relations that factorize the transfer matrix on this space in terms of transfer matrices over this product, and those are called Qs. So that's how the Verma module transfer matrix is related to a product of Qs. And then the second relation, I just use the fact that the trace over the middle is the sum of the traces over the two on the outside of the short exact sequence, and that implies these TQ relations at the bottom. Okay, and again, I'll go into a bit more detail, but in a nutshell, that's the Q operator construction. And it relies entirely upon these two algebraic properties of these different representations. So this is an infinite dimensional representation, this is a finite dimensional representation, and this is the full algebra representation, and everything else is a Borel subalgebra representation. So these are Borel subalgebra isomorphisms. Okay. And this idea has been now generalized to a higher rank. And in that case, you don't have Q-oscillator representations, but you have what Hernandez and Jimbo introduced, which they call pre-fundamental representations. And this approach is then being generalized to all untwisted quantum affine algebras. And the kind of triumphal success of this approach was by Frenkel and Hernandez in 2013, where they used this very general construction to prove some 30-year-old conjectures by Frenkel and Reshetikin about the form of the beta ansatz for these higher rank models. Okay, so that was a very nice consequence of this. And this, in turn, this algebraic approach has been at the heart of much recent work on QQ systems, Q-oppers, and all that. And if you want a couple of reviews that at least come from my side of the story, then there's Frenkel, Hernandez, and Frenkel, Jimbo, and Mukin talk about this. And this has also been partially extended to open systems, and that was fairly recently, and that's something I've been working on with Bart for several years. And this is all Q generic. So a lot is known about the Q generic case. I'm going to pause there. Any questions before? That was sort of the introduction. I'm going to go into more detail of this in the cyclic case. Okay, so that's the general picture. So let's go back to the roots of unity case. So although this Bajanov-Stroganov paper was the inspiration for a huge amount of this work, it hadn't been fully understood in this language. And in particular, the full role of the Borel subalgebra representations wasn't understood, with the exception of some early work by Korf from 2003 that did look at some Borel subalgebra short exact sequences. So I've revisited this work and tried to understand it in a slightly more modern language, or revisited Bajana-Stroganov. So what I find is I find completely analogous stories. So I look at these UQB plus cyclic representations, and now, so those are n-dimensional now. So instead of the Verma module, I think about the cyclic omega RS representations, and then I find completely parallel objects. So I find, so this representation depends on, so this representation depends upon two of these parameters in this algebraic curve, and I managed to factorize this into representations that depend upon just one parameter in this way. Okay, so and this is a UQB plus isomorphism. This thing is an even simpler version of this triangular representation. So this is now, it's an n-dimensional representation that is just the direct sum of n one-dimensional representations. So both the E0 and the E1 now kill vectors, but the Cartan doesn't. Okay. And then I find a short exact sequence. So if I specialize this value of Z in this evaluation parameter to be related to R, then generically this would be irreducible, but if I specialize Z in this way, I get this short exact sequence. And so what do I use this for? First of all, I use it to reinterpret Chiral Potts weights in terms of simpler objects just associated with these rows and row bars. And then I also use it to construct Q operators for the 6-vertex model and the tau 2 model. So that's the end of the introduction. Okay? So that's what I'm going to do. I'm going to tell you about these different representations and tell you about these isomorphism theorems and short exact sequences. Any questions before I hit you with the cyclic representations? Yeah? Yeah.
Of quantum affine.
You mean of the asymptotic algebra a la Frank Hernandez Jimbo? Is that what you mean? Shifted?
This particular case of shifted representations.
Yeah. Okay. So I haven't formulated it in that language, but I'm sure these could be lifted to a shifted representation. I mean, a representation of the shifted algebra, but not the full algebra still. I think that's the general picture. Okay, so these are the cyclic representations. So this works for Q, nth primitive root of unity, and for technical reasons, n is chosen as odd and greater than equal to 3. And this really comes directly from Date, Jimbo, Miki, Miwa from 91. So I've got an n-dimensional vector space, and then I've got this algebra, X and Z, the quantum toroidal algebra, and this is going to act faithfully on this space, W. And so X and Z satisfy these Q commutation relations and also this relation here. And then the Chiral Potts curve is the following. So I've got, so this is a complex algebraic curve. So X, Y, and mu are points in, each of them is in C, excluding the origin. And the algebraic curve is given by this. So this is this algebraic curve. This has genus n minus 1 squared. So if you look at n is 2, that corresponds to an elliptic curve. And then mu is given in this way. Okay. Okay. So k is the analog of the elliptic modulus. So that's the algebraic curve. And it was a great surprise originally when this turned up in a statistical mechanical model. People were used to R matrices that depended upon just complex numbers. So this algebraic curve was a surprise, and it was studied a lot. Okay, so then I'm going to give you the representations, omega RS, that depend upon 2 points in this algebraic curve down here. So I'm going to denote a point in the curve by R, and so this corresponds to a triple XR, YR, and mu R. And then I'm going to build representations of this algebra. So this is UQSL2 hat tilde, and the tilde just means it's you throw in 2 extra elements. You extend it by 2 extra elements. Okay, and these extra elements, these are group-like elements, and they come into the coproduct of the other generators in a fairly simple way. So, for example, the delta EI picks up this additional factor of this central factor here, and you can write down delta FI, etc. So rather than explain them, I'll just show them to you. So here they are, the representations. They're not particular. Well, they look horrible to start off with, but that's just because of the parameterization. So they're built in terms of x's and z's. So if you think of the z as a diagonal operator on this space, the Cartan parts are just in terms of z's, and then the e0s and e1s are in terms of x's, which shift up or down, and they also depend upon z in this way. Okay, so these were these new cyclic representations, and these x, and so each of them depends upon both r and s, these triples, x, y, mu in the Chiral Potts curve. And then, as I said, the R matrix of the model factorizes in this way. So here I'm completely swapping everything on the right and left. But I can do this by stages. So I take TRS, and this swaps, as you've shown, just this acts on one of these things. So this acts on one of these things and swaps R and S. And then SRS, it just swaps these middle ones here. Okay, so if you multiply this out in this way, you can check that it just takes all the indices around. So these are the factors. And the connection with Chiral Potts is just given at the bottom of the slide here. So if you write these as sort of discrete Fourier sums in terms of these z's and the tensor product of x inverse and x. So these were just the things that come into the representation up here, these n by n matrices. Then the coefficients are the Chiral Potts ones. Okay. Yeah. In which
representation?
So I've got R and S.
Yes.
And then I've got C0 inverse, which are the central, and then I've got a couple of kappa naught and kappa 1. Those are just fixed parameters that come into the representation. So they
some weight.
Yeah. So they're fixed once and for all.
I see.
So they're not.
And your algebraic, the relation is between x, y, and.
I'll show you again. So this is the algebraic curve. So K is fixed.
K is fixed.
And
U is okay.
Yep.
Okay, great.
Thanks. Okay. So really, they just depend upon these 2 points in the Chiral Potts curve, plus a bunch of other constants, which I haven't told you about. Okay, so these are these intertwiners. So these are horrible formula, and I like pictures, so I'm going to draw some pictures. Because I want to do things with these pictures. So omega RS, because it depends upon 2 points in this curve, I'm going to represent it by a double line. One red and blue for those who are colorblind. So these are R and S. And then so SRS, it acts in this way. It just swaps over the middle 2 lines. So it acts on this tensor product and just swaps this and this. So the picture is it just does something non-trivial here. I just say it's hand recognition that I've somehow got switched on. And then TRS just swaps over 2 of these. So then you can build the R matrix, and you get this picture at the bottom. It's a product of 4 of these things, if you stare at it. So you've got 4 of these different objects in there. So secretly in here, there are 2 different things. There's a T and there's an S, and then down the bottom, there's a T and S. So anybody who is familiar with Chiral Potts might be slightly surprised at this picture, because in the literature, you see a picture of this where you would take this line here and drag it down, and you get separated lines. But I don't like that diagrammatics. It's confusing, and it's confusing because in the diagrammatics, separation means tensor product, and also I mean something by individual lines as well. So I will have a tensor product of two lines which are separated. So to distinguish it, I join these two lines together for my omega. That's just for people who are used to Chiral Potts pictures. Anyway, it's the same story. Okay, so that's all was all known. So then what I do is I invent these cyclic representations of the Borel subalgebra that play the role of the Q-oscillator representations. And these are really easy to write down representations like this. Again, it looks unpleasant because I have these coefficients here. But the essence of this is that one of these goes up and one of them goes down. And the only relation I've got now is the Serre relation. So those trivially obey the Serre relations because they commute, E0 and E1. And then you've just got the relation with the Cartan, and that works because of the Q torus behavior. So these are very easy representations to write down. And then there's an even easier representation to write down, which is this thing, which is this n-dimensional representation, which is just the sum over one-dimensional representations, because on each of these, the e's, noughts, and e1s give 0. Okay? But the z's are just diagonal. Okay, so these are the pictures corresponding to those. You've got to remember the pictures. Okay, so I've got rho r is red, and rho r bar is blue, and then the very simple thing has dots. Okay. Okay, so then here's a theorem, and this is the analog of this factorization theorem I had before, and it's really very simple. So there's a U B plus isomorphism between the tensor product of this and this very simple representation. And when I say simple, I mean not complicated. It's not simple. The tensor product of this is just isomorphic to these things. So what this does is it splits up the dependence upon two parameters into the tensor product of things that just depend upon one parameter. And it's a really, really simple operator, so it just depends upon x inverse and x in this way. So it's just a polynomial in this. And so diagrammatically, I represent this by a blob. And so these pictures act from left to right. So this is omega rs that depends upon, has two lines, and it splits up these lines. So that's the picture, and it's an isomorphism, so I can write down an inverse picture as well. Okay, so that's the factorization theorem. And there's an immediate consequence of this, which is the following, that I have these following isomorphisms as well. And I'll tell you why I think these are important after just explaining them a bit. So let's look at where these come from. So this is almost trivial. So it's just saying if I start on this and then I act with my inverse blob, it turns me into an omega tensor something. Then I act on the omega with the t, and then I undo it. So this isn't particularly deep. It's just saying I can use this omega to O operator to turn this operator, which acted on a single omega, to something that just changes this to this. And so that's clear. This one isn't quite so clear, but essentially, well, it does this at the bottom. Okay, so you can check and it does this. And so pictorially, these are just given by these simple intertwiners. These are not quite, R matrices still, because they're not, because it swaps the R's and the S's, but the hats, the bars, stay in the same place. So it's not just that it turns something into that, so they're not quite projections of some, if it exists, universal R object. I mean, representations, they're not that. But nevertheless, they're extremely simple objects. And so in retrospect, I think maybe this is the most important thing in this paper. It's very, very simple. But what it does is it gives a very simple picture of the Chiral Potts weights, right? So these just encode Chiral Potts weights. So Chiral Potts weights are this. Okay. Yeah. So P is so what? Okay. So if you think of this taking omega tensor omega, then you think in the middle you have a rho bar tensor rho, So what P does is, I'll show it in terms of L operators in a minute, and then I think you will understand immediately what P does. Yeah. Okay. Okay. So that's what I call factorization. Fusion. So fusion is physics language for short exact sequences. So and here they are. Okay. So VZ is the two-dimensional standard two-dimensional evaluation representation. And then if you look at these UQB plus short exact sequences exist. Okay, so I take a tensor product of these things with VZ, where Z is S, so it's the ZS that just depends upon the point S in this way. So these exist. This last one appeared in Korf's paper in 2003, but he didn't consider rho and rho bar. So again, I like pictures. So these are the pictures. So the iota, the embedding, and the projection, I just view them as acting from the left in this way, in a fairly obvious way. So if you compose two of these things, then they would give 0 because of the short the exactness, right? So there are these operators that do this and this. Now on to L operators. I want to get to transfer matrices eventually. So I finish at 10 o'clock, do I? So what time do I finish? 10 minutes. Okay. Okay, so L operators. So what are L operators? L operators are intertwiners where you choose one of the representations to be this two-dimensional evaluation representation. Okay, so I can write down these 4 intertwiners. The top left one is a full quantum affine intertwiner. The rest are just UQB plus intertwiners. Okay? And so I can just compute what the L operators look like. And because I've got this two-dimensional representation in the vertical space, I can express these L operators as 2 by 2 matrices that act in the horizontal space. And if you do that, then all of these L operators have a very nice, simple form. And the form is the following. And I learned this paper from Yuan, Miao, and Lamas and Pasquier. But something similar also, I think, occurs in the Derkachov paper. So they all have an extremely simple form of the following. So to answer your question, what is P? Imagine taking the tensor product of this and this. So the thing that shifts this to this, that's what P does. And the level of L operators. Okay. Good. So these are the L operators, and I can write them down, and then I can look at the properties of these things that follow from these factorization and fusion formulas. And these are the formulas, and I find these easier to understand pictorially. So let's pick the first one apart. So why are these two things equal? These two things are basically equal because of the uniqueness of the UQB plus intertwiner. Okay, so the left-hand side is a particular UQB plus intertwiner. You argue that it's unique, and so these two things have to be equal up to a constant. And that similar argument occurs in the bottom. So here I look at this intertwiner that goes from this to this. And again, you argue uniqueness and show that it has to be equal to this. And physically, it just means you can move these green lines through things. Okay, the vertical lines. So these follow, and so these just really follow from uniqueness arguments plus the intertwining, the factorization and fusion that I built algebraically. And then there are these two innocuous-looking parameters that come in here, but actually all the physics is buried in these two innocuous-looking parameters. And for those, well, in fact, what they're actually given by is they're given by the weights in the 6-vertex model. Okay, so the reason these are so important is that these relations immediately lead to TQ relations with certain coefficients that give you beta ansatz equations. So these coefficients are the coefficients that are in the beta ansatz equation. So all the physics is somehow sitting in these. Okay, which brings me on to transfer matrices and Q operators. So what do you do? So how do you build a transfer matrix? It's a recipe. You take the product of L operators and you take the trace over the horizontal space. And I also put in this twist by Carter element in here. So this is a twist that I don't draw pictorially. So So the simplest transfer matrix is just the 6-vertex transfer matrix, and you get that by taking a product of m of these things and then taking a trace over the horizontal space with this twist inserted. But then you can change the horizontal space to any of the representations that I've looked at previously. And so I do that. So I can choose this to be rho, in which case I get Q rho and rho bar, and I get this other object T omega RS. And then finally I can do it with this simple thing, and I get this and so the L operator is diagonal in this really simple case, which means that this thing is also diagonal, and it just depends upon the weight or spin sector of the theory. So this thing at the bottom is extremely simple, all right? So that's the recipe from how to get to algebra to physics. You work out L operators, you compute transfer matrices. And then immediately you get a bunch of properties for transfer matrices that just come from the properties from L operators that in turn come from the algebraic properties. So here's the diagrammatic proof, of this formula for writing T omega in terms of a product of Qs. So this was a composition in this direction of T phi and T omega, but I can insert these UQB plus intertwiners in this space. Then I can pull them through L operators using the relations I wrote down, and then I get the trace or something times its inverse, so the blobs disappear. So I end up with this diagrammatic proof that T omega T phi is Q. Okay. And then I won't tie you with a picture, but there is a picture. So if I look at these short exact sequences and I take the traces over the different spaces, horizontal spaces, then this trace over this place splits up into a trace over this plus a trace over this, and that immediately leads to TQ relations. Okay, and again, these coefficients that occur here are the standard 6-vertex model Boltzmann weights. Yeah. Yep.
So the Q rho bar is sort of the Q bar.
Correct. That's the picture. Yeah. Okay, and then what do you do? So the next step, if you're a physicist, is you take these models, you derive beta ansatz from this in a one-line derivation, and then you spend 5 years solving the beta ansatz equations. Okay, but I'm not going to do that because I'm going to pretend I'm a mathematician and leave that to somebody else. So I also get from this. You can also play this game, and you also get a short a TQ relation type object for this. And so this T omega are exactly the same TQ relations as the Q and the Q bar, and this comes from this short exact sequence. And this fact that this object satisfies the TQ relation was actually in the original Bajorov-Stroganov paper. One thing I should comment on is why have I included a twist? So when I include infinite dimensional representations, you put in a twist to make your trace convergent. Now I need to put in a twist for a different reason, because otherwise I get that this is true. So I want to stop things being equal to 0, so I put in a twist for that. Okay, I'm almost done. So you can change the quantum space as well. Oh, that's weird. I don't see that. What happened then? I what? I went out of Zoom. Okay. I should get back into. Oh, did I? US screen sharing? Stop sharing? I could stop share and start again. Screen broadcasting. Live broadcast has stopped due to you have stopped screen sharing. No, I haven't. Okay. Stop broadcast. Enable do not disturb to prevent unexpected notifications.
Recording in progress.
So now it's good. Okay. I'm sharing. You're listening. Okay. Good. So I can play the game. I can change my quantum space as well. I can write down L operators in this way, and I can define an operator that acts on this quantum space that looks like this. So this is an operator that had been studied before, where it's called the transfer matrix of the tau2 model. And this was introduced early on by Baxter, I think, in discussing Chiral Potts model. And then I can also look at this object, and because I know the short exact sequence for these two spaces, I can write down a similar TQ relation for this. Okay. And then the full Chiral Potts transfer matrix is this, and so it sort of is the suitably interpreted product of this Q and the Q bar. And so originally in Bajanov's and Stroganov's paper, there was an observation that the Q operator of the tau2 model, the thing was related to the half transfer matrix of the Chiral Potts. This explains that. Okay. For those who know. Okay, so discussion. So we've got, so the key result was this factorization result that I can separate out these dependence on RNS, and I also get these short exact sequences, and as a consequence of that, almost immediately you get this T factorization into Q and Q bar, or Q rho bar, and you get TQ relations. So one difference with the generic case is that you can, well, in the generic case, you can derive this relation from this by using the BGG resolution. So you can look at the Verma module and show that a quotient of the Verma module is isomorphic to the two-dimensional module. And so you can derive this from this. In this case, we can't do that. We don't have a BGG resolution. But according to Yuan and friends, they managed to, I should say that, you know, there has been similar work at the level of L operators from Yuan, that, and although they're considering semi-cyclic representations, I understand, and in that context, they do have something that looks like the BGG resolution, although we need to discuss why it's the case. But in principle, we can get semi-cyclic by taking a limit of our cyclic representations, and that was actually done by Uglov in '92, actually. They looked at semi-cyclic representations. So why am I doing this? One is interest, but the other one, I think it's called, you know, by youth, a side quest. Okay, so my main quest is, for the last few years, has been understanding open Q operators. And that's an ongoing project. And we have factorization formulas for the open case with particular boundary conditions of this form. But there are various complications that arise. And essentially, all those complications are to do with the infinite dimensional spaces involved. So there are two real problems. One is solving the reflection equations for the infinite dimensional representations is quite tricky for general boundary conditions, apart from very simple cases. And the other one is convergence of these infinite dimensional traces. And so one of my motivations for looking at this finite dimensional encode is that I don't have to worry about some of these problems. There are other problems. So that was partly why I've been doing this. So one of the things we're going to do now is look at the open Q operators for these cyclic representations. Thank you.
Thank you for your talk. Do you have questions?
I have a question just about the beginning of your talk.
Yes.
The statement of the problem. If you consider the factorizable polyvector.
Factorizable
polyvector.
Polyvector.
It is equivalent to the Blücher equation.
Right.
Does it make sense for more complex structure like factorizable transfer matrix or Mondrian matrices?
Yeah, I hadn't thought about that at all, but interesting question.
Other questions? Okay, can you explain me a little bit what's the current status of Q operators in the open span chain case? So what we know, what we don't know, what we want to get.
Well, there are sort of different aspects of that. One is about universal objects and universal K-matrices, which, thanks to Bart and Andrea Appel, their existence has been shown for general coordinate subalgebras. So existence of general universal K-matrices is known. So we have an actual construction using very similar ideas for diagonal K-matrices. So we have constructed Q operators for diagonal K-matrices. For the off-diagonal case, very little is known about actual construction. There's work on for the triangular K-matrix by Kujima and Basaik, and I think, yeah. But in general, there's not too much is known. So this algebraic construction using Q-oscillator representations, and so we have a boundary factorization formula as well. We have factorization of how these embeddings and projections talk to the boundary. We have results on that, and that is not boundary specific. So we don't see why any of what we're doing should fail in the off-diagonal cases, but we haven't done it yet. So.
What if we restrict ourselves only diagonal to K-matrices and fundamental presentation, tensor product fundamental presentation, spin chain, like
for
usual
the transformatrix or for the Q operator?
Q operators, of course. Transformatrix I know a little bit.
Yeah, so transformatrix is very, very well known, although the beta ansatz, even then, there are still questions about the form of the beta ansatz, and the main form is a conjecture still.
Yeah, but Q operators.
But the Q operator, the only case where there's explicit construction really is the diagonal case, which is what we've done, and also Suboy has done something very similar. So the diagonal K-matrix is only diagonal is what we've done so far.
So it's done?
Yes, that exists. For SL2.
SL2,
yeah,
of course.
Yeah.
For today. Okay. Thank you.
Okay, thank you.